this video, we're going to talk about the fourth colligative property, which is osmotic pressure. So osmosis is the flow of a solvent into a solution through a semi-permeable membrane. So if we have a solution and then we have a membrane between the two of them, and we have a solution on either side, and this side is less concentrated, and this side is more concentrated, then what will happen is, if we have a semi-permeable membrane here, the semi-permeable membrane will allow solvent molecules to go through, but not solute molecules. And we will go from an area of less concentration to an area of more concentration, so that we end up diluting the area that is more concentrated. But only the solvent gets through this membrane, not the solute particles that are in the less concentrated solution. Osmotic pressure is a result of the increased pressure as we add more solution, as we add more solvent to the solution on this side of the membrane. So we're putting more liquid into the space, which increases the pressure. So for example, if we have our flask here that contains a solution, and we have our pure solvent on the outside here, so the pure solvent is obviously going to have a lower concentration than the solution, because the solvent has nothing dissolved in it. And then we have our semi-permeable membrane here. The semi-permeable membrane allows the solvent to flow through. So over time, what's going to happen is the pure solvent is going to pass through the membrane into the solution in the flask. Eventually, we're going to get to a point where we just keep adding more solution. So we've got more liquid in this flask, which is going to increase the osmotic pressure. So we can determine what the osmotic pressure is by applying pressure to the solution and determining how much pressure we need to stop the process of osmosis. Osmotic pressure has a lot of uses. If we want to move some solvent and filter out the solvent and get solute by itself, that's one way to do it. We can use this as a way to characterize solutions. Sometimes we can do it as a way to calculate the molar mass of something that we need to determine the mass of. Or we can use it as a way to calculate osmotic pressure on a solution and use that to determine concentrations of molar masses. So let's actually look at an example. Before we get there, we have to talk about the equation. So of course there's an equation for osmotic pressure. The equation that shows us osmotic pressure, this is the symbol for osmotic pressure. That's equal to the molarity of the solution times the gas law constant times the temperature in Kelvin. And because we're using the gas law constant here, which has units of liters times ATM over Kelvin times mole, osmotic pressure has to be in ATM. So let's look at an example here where we try to determine molar mass using osmotic pressure. So the question tells us to determine the molar mass of a certain protein. 1 times 10 to the negative 3 grams of it was dissolved in enough water to make 1 milliliter of solution. The osmotic pressure of this solution was found to be 1.12 torr at 25 degrees Celsius. Calculate the molar mass of the protein. So we know osmotic pressure has to be in ATM. So the first thing that we need to do is convert this 1.12 ATM to torr. Sorry, this 1.12 torr to ATM. So if you think back to gas pressures and the conversions, 1 ATM is equal to 760 torr. And you could look that up if you didn't remember the conversion. On a quiz or an exam, you would be given that information, so you don't need to memorize the conversion there. So we have 760 torr. .12 divided that by 760 is equal to 0.00147 ATM. The molarity is what we're trying to calculate. R, the gas constant that we're going to use for the equation for osmotic pressure, is 0.08206 liters times ATM over Kelvin times mole. And the temperature is given to us is 25 degrees Celsius. And we have to convert that to Kelvin. So to convert to Kelvin, we add 273. So 25 plus 273 gives us 298 Kelvin. So then what we need to do is plug what we have in and calculate in. So I'm going to erase some of this here so that I have enough room to work out the rest of this. So osmotic pressure is equal to the molarity times the gas law constant times the temperature. We want the molarity, so I'm going to rearrange this equation algebraically to get molarity by itself. So molarity would be equal to the osmotic pressure over R times T. And we calculated the osmotic pressure as 0.00147 ATM over 0.08206 and the temperature in Kelvin is 298 Kelvin. So 0.00147 divided by 0.08206 times 298 comes out to 6.03 times 10 to the negative 5th ATM. So we're not quite done yet because we calculated the molarity. The question wants to know the molar mass of this protein. So the next thing that we need to do is we need to calculate how many moles we have and then use that to get molar mass. So what we're going to do is I'm going to erase, I'll erase where we calculated the pressure here. And I'll also erase this conversion. So if we take, oops, that is not ATM. That is molar. So if we take 6.03 times 10 to the negative 5th, So molarity is moles per liter. So this means that we have 6.03 times 10 to the negative fifth moles per 1 liter. And we're told in the equation that we did this and dissolve this protein in enough water to make 1 milliliter of solution. So 1 milliliter, we need to convert this to liters. So 1 divided by 1,000 would give us 0.001 liters. So 6.03 times 10 to the negative fifth times 0.001 equals 6.03 times 10 to the negative eighth moles. And then in our last step, we have 1.003 times 10 to the negative 3 grams. So molar mass is in grams per mole. So we can take 1.00 times 10 to the negative 3 grams and divide that by 6.03 times 10 to the negative eighth moles. And if we divide that out, that comes out to 16,600 grams per mole. Or you could write in a scientific notation as 1.66 times 10 to the negative fourth times 10 to the negative fourth grams per mole. So that seems like a rather large molar mass, but that's actually pretty small for a protein. Proteins usually do have a fairly high molar mass. So don't think that your answer coming out that way means that you did something wrong. It's just coming out that large because we're dealing with a protein here. So this is one way we can use osmotic pressure. That by calculating the osmotic pressure or measuring the osmotic pressure of the solution, they know how much protein they dissolved in water. So then we can use the equation for osmotic pressure to calculate the molar mass of this protein. So there's a lot of uses of osmosis. One way that it's used actually in your body is it's a way that your cells allow certain things in and keep other things out. So solvent molecules can get through, so things like water, for example, when that's appropriate. Small solute molecules that are small enough to pass through the membrane can get through, but things that you don't want to get into your cells can be kept out. They're also useful in medicine for things like dialysis. That's how we use artificial kidney machines to do the work when someone's kidneys aren't functioning properly. That's how dialysis is able to filter out the waste and toxins in your blood much the way your kidneys do. We can also use reverse osmosis or cause reverse osmosis. So when you take a solution and you have a solution with solute particles in it and you want just the pure solvent, what you can do is subject the solution to a pressure that's higher than its osmotic pressure, and that will force things to go in reverse across the semi-permeable membrane so that we get pure solvent and the solute particles are kept out. So this can be used for things like filtering water. For example, if you have seawater that has a lot of salt and particles in it, and you're trying to get rid of some of those different salts and different things that are dissolved in the water, you can use reverse osmosis and you would get a lot of the salts that are dissolved and other things that are dissolved in seawater. You can also use it in water filters when you're trying to filter out certain particles. So this is kind of what I was talking about. Then you have seawater from the ocean. This can be forced through a desalination device, which uses the principle of reverse osmosis to get rid of all those salts and other things that are dissolved, and we get fresh water that's pumped out that we can actually use. So the equation that we talked about for osmosis, and actually for some of the other colligative properties, they don't take into account the fact that ionic compounds produce more moles of solutes than we actually dissolved. So for example, if you have something like sodium chloride does not just dissolve into sodium chloride molecules floating around in solution. You get sodium ions and you get chlorine ions. So we actually get 2 moles worth of ions out of this 1 mole that gets dissolved. So we have to add what we call the Van 't Hoff factor to these equations. That gives us the relationship between the moles of solute that are dissolved and the moles of particles in solution. So the equation for the Van 't Hoff factor is moles of particles in solution divided by moles of solute dissolved. But often the moles of solute dissolved is just 1 mole. So essentially, the expected value for I is how many ions we would get out of that ionic compound. So for something like sodium chloride, it would be 2. For something like magnesium chloride, where we would get magnesium and 2 chlorines, the expected Van 't Hoff factor would be 3, because we have 1 mole of magnesium ions and 2 moles of chlorine ions. So the change in boiling point and change in freezing point that we calculated earlier, we can add the Van 't Hoff factor to those equations. And similarly for osmotic pressure. So let's take a look at an example on how we would use this for osmotic pressure. The observed osmotic pressure for a 0.10 molar solution of iron ammonium sulfate at 25 degrees Celsius is 10.8 atm. And we want to compare the expected and experimental values for I. So for the expected, if we put this compound in solution, what we would expect to get would be the ions. So we would get iron, see sulfur, so iron 2 positive plus 2 ammonium ions, plus 2 sulfate ions. So 1 mole of iron ions plus 2 moles of ammonium ions plus 2 moles of sulfate ions. Our expected value for I would be 5. Now let's see if that's actually what our value for I is when we plug these values in. So I'm going to go ahead and rearrange this so that I have less writing to do later on. So the osmotic pressure as given to us is 10.8 atm. We have a 0.10 molar solution, 0.08206 liters times atm over Kelvin times mole. And 25 plus 273 is 298 Kelvin. So if we divide this out, 10.8 divided by 0.10 times 0.08206 times 298, close your parentheses, 4.4 should be what you come up with. So the expected value would be 5. The experimental value based on the osmotic pressure that we get for a 0.10 molar solution at 25 degrees Celsius is 4.4. And this is probably due to some ion pairing that goes on in solution that we're not accounting for when we just count up the ions here. So the last thing that we're going to talk about to do with solutions here is something that's kind of similar but not exactly the same thing. So colloids are similar to solutions in that we have things mixed together. Rather than being dissolved in the solution, it's actually a suspension of tiny particles in something else. So they can be rather small, things as small as 1 nanometer, or we can have aggregates up to 1,000 nanometers. So there are different types of colloids depending on how they're dispersed, depending on what phase they're dispersed in and what medium they're dispersed in. So there's a few different examples. Things like aerosol sprays are actually colloids. So there's a liquid dispersed in a gas, and it sprays out the way that you want it to. So things like those sprays that have different scents, or things like hairspray, are actually colloids. Smoke is actually a colloid. It's a solid dispersed in a gas. Things like mayonnaise and milk and whipped cream are all colloids. Things like milk and mayonnaise would be a liquid that's dispersed in a liquid, whereas something like whipped cream would be a gas dispersed in a liquid. Even some of the foods that you eat, things like marshmallows or cheese or butter, are all colloids. So this is just another type of way of classifying matter. They're similar to the idea of solutions in that we mix things together, but a colloid is dispersed in something rather than actually being dissolved in it. So we will wrap up here, and we will get some more practice with osmosis and colloidal properties and colloids in class. So I will see you in class.